What's going on, everybody? This is Mr. Diamond, and we're going to be doing the last two examples that I have for you, which are the impulse examples. This video will be pretty short, but it's just explaining how to do problems relating to impulse, and one involving kinetic energy, because I don't think I did one in the other section. So if you'd like to pause the video and attempt to do these two problems by yourself, you can. I'm going to read them, and then after that, I'm going to get right into the problem. So this is example number 4. We did 3 in the momentum section. So example number 4. A karate master strikes a board with his 0.95 kilogram hand at a speed of 12 meters per second. The motion takes 0.1 seconds, breaking the board in half. Determine the impulse and the force of the hand. And then number 5 is determine the kinetic energy of a bullet fired with an impulse of 25,000 newtons per times seconds, or newton seconds, and a mass of 0.08 kilograms. So if you want to attempt them, pause the video now. Otherwise, we're going to get right into it. So for question number 4, the relevant information we have is we know that impulse is equal to the change in momentum, and we know equations for both of those. In this case, impulse had the equation that we gave it in class, or I guess not technically in class, is equal to change in force over time, or the sum of the force over time, but we were given speed and we are given a weight. Now, this is a speed of the karate chop as it's happening. So something that's kind of useful for this chapter is I'm going to draw a really crappy stick person. That's not the specific piece that's relevant for this chapter. But we're going to call this the board, and they are striking the board. They're going to karate chop their hand. And so their first part they're going to be doing is moving their hand downwards. And then in the second part, after they have broken the board and their hand has extended for some reason, and the board is now broken in half, when you chop, you move your hand and then you stop it after it has passed through. So we actually know a V naught is the original motion that it tells us. It's going to originally be moving at 12 meters per second. But after breaking the board, and even at the exact moment that it's at impact with the board, it would have a final velocity of 0. I know I've been using V1 and V2. I apologize that I keep kind of flipping back and forth between them here. Let me switch to V1 and V2 just to try to stay a little bit more consistent. And we also know a mass. Mass is equal to 0.95 kilograms. And we know a time. And time is equal to 0.1 seconds. Now, I got a little distracted from my original point up here. Let's scoot this up so it can maybe be in focus a little better. It's weird that the bottom is a little bit more out of focus, but whatever. So our momentum equation, our change in momentum, is equal to mass times change in velocity. And in this case, we have our two velocities and we have a mass, so we know our impulse must be equal to 0.95 times, and then we remember we do final minus initial, so 0 minus 12 meters per second. 0.95 times negative 12 will give us negative 11.4 Newton seconds. Now that might feel a little bit weird, but remember the hand is stopping. Hand stops. So stopping, or so direction is negative. The force that's acting on it when you stop your hand is inhibiting you. It's preventing the thing from occurring. And if we assume that going down is the positive direction, in the case of chopping, or that moving forward is the chop, with the chop is the positive direction, stopping would have to be against it. It would have to be the negative direction. The second part of the question then asks for what is the sum of the force. And thankfully, we know that impulse, which again is equal to change in momentum, impulse is equal to sum of the force times time. And in this case, we have time, so our impulse must be equal to, or if we rearrange it, sum of our force must be equal to impulse divided by time, which is negative 11.4 divided by 0.1, which we know that just moves the decimal over. So the force is going to be negative 11, or 1,114 newtons. And again, it's a negative force, but that's just because it is it's stopping. It's a force preventing it from moving and making it slow down and stop. Okay, for question number 5. Question number 5. Let me get this situated. Oh, I think I made it focus a little better. I wish I would have done that earlier. So we want to know, what is the KE of a bullet? And we know that the impulse is 25,000 newtons per second. And we know that the mass is 0.08 kilograms. So now we're going to use that same setup as before. Impulse equals change in momentum, because that's really the only step we go. For kinetic energy, we need 1/2 mv squared. So we need to have a mass, we need to have velocity. We don't have mass, or we have mass, but we don't have velocity. And our impulse / momentum relationship equation, if we write that full thing out like we did kind of up there, we'll get m delta v equals sum of the forces over time. And notice we don't need this piece. This piece is just impulse. But we want to find these two pieces. We already have mass. We're trying to find that change in velocity. So we can say that the change in velocity, in this case, must be equal to impulse divided by mass. And our impulse in this case being 25,000, our mass in this case being 0.08 kilograms. We get a very large number that is very unrealistic, 312,500 meters per second. Definitely not, definitely not going to be accurate, but we don't need to worry about that for this problem. We're just going to continue solving it through. So that's our velocity. So our kinetic energy at the end here is 1/2 mv squared. We get 1/2 times 0.08 times 312,500 squared. And then plugging that in, you get the very large number, which again is not realistic, but 3.906 times 10 to the 9th joules of energy. That must be the joules of energy that it has. And we know this must be the answer if we think about, technically we solved for delta V, so the change in velocity, but remember that would be V2 minus V1, and we know that the bullet before being fired was at rest, so the only thing that could have added to that, something minus 0, would have just been the same thing. It would have been 312,500. Again, very unrealistic. I think I looked up a table of impulse for bullets, and after doing this once, I realized it was not very accurate, but, you know, well, what are you going to do? That's what I get for getting my information off the internet. All right, these are the impulse examples. This should, between the notes videos, the momentum examples, and these impulse examples, give you enough to be able to work on the momentum and impulse worksheet this week. If you have any questions, please shoot me an email. Otherwise, stay safe out there, everybody. Have a good rest of your day, and I just hope to see or hear from you soon.